in our first video in our journey on our Eternity series, we took a look at sunlight. And sunlight was like a little gentle reminder that we see each day of a beautiful hidden curve. And so even though sometimes what we see is discrete things, there's something that's bigger behind the scenes. It's like a video. And so in this video, what we're going to do is we're going to go from what we see to what we hear. Now, things that we hear are also discrete. Think about the words that we say. Those are discrete words. But how about the things we hear that are beautiful? Is there a pattern to this beauty that's behind what we hear? Well, nature has given our eyes a gift of sunlight. So is there a gift that nature has given to us that is a gift to our ears?
We have our Pentatonic Chimes over here. What is it about this particular set of chimes that makes it beautiful as opposed to other chimes?
Not all wind chimes are created alike, and they're not equal. This particular set of chimes has a pentatonic scale, as you mentioned, and so the different chimes are tuned to specific pitches that when they play, even randomly by the wind, they create pleasing sounds. The pentatonic scale includes 5 different notes, hence pentatonic, 5 tones, and they include the do, re, mi, so, and la pitches of our scale.
You were missing some in there, I think.
Yes, well, if you look at the Western scale, the ones that we are so accustomed to growing up, you've got, like these chimes here laid out, do, re, mi, fa, sol, la, ti, do. And that's a 7-tone scale. When we get back to the top one here, we're just repeating the cycle. So I'm going to move that one out of the way. And now we have 7 tones that we're used to in the diatonic scale, our major scales, our minor scales. The pentatonic scale only has 5, so we have to remove 2 of them. And there are not equal pitches between the, equal distances between these pitches. For instance, between the E and the F, there's a half step, and between B and the high C, there's a whole step again. So if we separate them like this and isolate only the do, re, mi, so, la, do, re, mi, so, la, that's our pentatonic scale. It does sound like that, yes. 5 tones that are distant enough from each other that they sound good no matter how they're played.
So you talked about the relationships between the notes being what makes them sound good or not. Why did we add those other 2 tones into our 7-note scale?
Well, they create what we call tension and release. A lot of the music that we have in our Western culture, European culture, is based on phrases that lead us to a point of tension temporarily that we yearn for to be resolved. For instance, the high pitch T here resolves upward to the high do. We feel that pulling us that way. Similarly, the fa pitch here, F, resolves in a downward direction. So we have that tension that then resolves. And it sounds pleasing to us. And it actually kind of tells a story where we set up a phrase and it starts to build and develop and gets to a point of tension, and then we want it to move forward some more until it comes to a place of rest, to the home tone, back to the tonic scale, that resolution. And that's not unlike it is in God's creation too. If you think about all the times when we experience tension, what do we long for? We long for that to be resolved, for it to move forward. So our scales kind of tell that story of the human struggle of setting up a tension, a tense situation, some suspense that eventually moves then towards a satisfying resolution.
So if the 5 notes in the pentatonic scale seem more satisfying to us, is that something that we find across cultures? Does everybody gravitate toward those 5 tones in the pentatonic scale, or do we all kind of like different things?
It's important to note, I think, that in our diatonic scale here, that the pentatonic scale is still there, right? We still have the 5 tones that create the pentatonic scale, but we've just added some and embellished some. In our culture, that's become the way we move our music forward. But many cultures of the world are based primarily on the pentatonic scale. In Africa, in Asia, in South America, throughout the world, the pentatonic scale is ubiquitous. We find it everywhere. And it has a more sonorous sound, more pleasing, and almost more freeing in that we are able to improvise. without fear of playing the wrong note, without fear of creating some dissonance. And you'll find people that back away from the diatonic scale saying, well, I might hit the wrong note, I may play it incorrectly. Whereas the pentatonic scale, there are no wrong notes. Hence why they're used in wind chimes, because that random sound still is pleasing to our ears.
So we mentioned the set of chimes is in the key of C, right? That's the chimes that you have here, the same notes. If I start with one chime and I know it's C, how do I make sure that the rest of my notes are the right 5 notes to form the pentatonic scale?
Yep, depending on where you start, if you have your home tone, your tonic, for instance, in the key of D, instead of starting with C, if we started with D, you would want to go a whole step higher for the 2nd degree, and then you'd go another whole step, and then you go a minor third from that one to the 4th degree of the scale, and another whole step to the 5th degree, which is universal. It will fill up any place you start. If you start with a G, it would be G, A, B, C, and D. If you start with that D, it's D, E, F sharp, A, and B. And you can create a pentatonic scale regardless of where you begin. Yeah.
So you just have to make sure that the relationship between the notes is the right spacing.
Yes, and there's scientific, mathematical reasons for why that spacing is pleasing to us and why the pentatonic scale is so popular and available to so many cultures in the world.
Neat.
The pentatonic scale is great for improvising and for freely creating music that goes with any other pentatonic scales. And so if we take out those semitones again, those half steps, and we're left with just the pentatonic scale, it's going to sound pleasing to our ears. And you can make up any little tune there. People who have the pentatonic scale experience less stress about hitting the wrong notes. And even when you're playing the piano, if you get somebody who has all the white keys or all the piano, they make noises, it doesn't sound, there may be some dissonances there that's not pleasing, and it's pretty obvious that they haven't had any training. But if you only use the black keys of the piano, which are naturally arranged in a pentatonic scale, and you ask them only to play the black keys, it's going to sound pleasing no matter how they play it.
Right, you don't have to be trained.
No, and which is very freeing for creative people or people who think that they're not musical to know that it's accessible in a way that God just created this naturally arranged set of pitches that sound good to us.
Maybe there's something there then that it's beautiful in part because it's accessible to all.
Good point.
Something about the mathematical arrangement of these different tones, the way that the lengths of the chimes relate to one another, we hear that and interpret it as beautiful. Where did that come from? How are we just designed that that's beautiful to us?
There's been a lot of research about that and experiments checking to see if perhaps the pentatonic scale has some qualities about it that are innate in all of humankind, that God created us to be attracted to these tones for whatever reason, whether it's mathematical, scientific, has to do with our perception of sound. We gravitate towards it and recognize it as pleasing and almost natural, part of society and nature. Even if you listen to many animals and bird calls in particular and things, they use tones that are present in the pentatonic scale.
Wow.
So it just seems to be part of nature, part of God's plan and design in His world.
And you mentioned how even in the diatonic scale we see the pattern of those added notes add tension, but it's looking forward to the release. I think there's maybe some parallels to the tension that we see in the world around us, looking forward to that release that God will bring.
Absolutely. Yeah, there's the idea that we would add these other notes. They are only there to call attention to the resolution. And so that feeling of tension or strife is only temporary. And there's something within the human condition that longs for the resolution, not unlike our what we look forward to, resolution in our lives.
We can all sing pentatonic together.
There you go. I've tried that. It works pretty well.
Well, that was really cool hearing Paul talk about the chimes. And now we've magically brought these chimes in here. And what we've got here, let's just take a look at two of the chimes. We're going to take the longest one, this guy right here, and the shortest one. They're both play the note C. They're 1 octave apart. Their frequencies are double, but as you can see, their height is not double. So you wonder, well, why are they not double? Well, we're going to talk about that. But first, we got these two blocks. This block is actually correlated with this chime, where this one is 23 inches, and then this one's converted to 23 centimeters. So they're the same after we convert from inches to centimeters. And then likewise for the smaller chime, we converted the length of this chime from inches to centimeters, and that matches this block here. So now we have two blocks that are correlated with the chimes in height, just converted from inches to centimeters. So now we're down to 2 blocks, and that's what math people like to do, is working with blocks like this. So how do these two correlate? How do they connect to each other? Why is one twice the other? So look, I'll let you have that one here. And as you notice, that's a square. So what is the formula, Jack, for the area of a square?
Well, it's just length times width.
Length times width. Okay, so we got the same thing here. This one's smaller than the other. But if we bring in a second block that looks exactly like the first, now what we have is we can think about maybe like volume, because we have length times width, then times 2, because it's too high, and that's length times width times 1.
Yep.
Still volume, but we're comparing volumes. And the volumes of these two shapes are exactly the same. And so that's why we know the size of that smaller chime must be exactly that length, is because that's the length that gives us equal volumes between these two squares. To understand why the volume of one yellow block must equal the volume of 2 green blocks, let's explore the relationship between musical notes, frequency, wavelength, and chime length. Take a peek at the table of the complete musical scale between A4 and A5. The frequencies 440 Hz and 880 Hz both correspond to the musical note A, but they're 1 octave apart. An octave means a factor of 2 in frequency. So the A4 note has a frequency of 440 Hz, and then when we multiply it by 2, we get 880 Hz, which corresponds to A that is 1 octave higher. So how many notes are there in 1 octave? As you can see from the table, we have 12 notes in 1 octave. To go from one note to the next, simply multiply the frequency of the lower note by the 12th root of 2. For example, if we want to go from B to D, since there are 3 notes apart, we multiply the frequency of B by 2 to the power of 3/12 to get 587 Hz. Next, let's explore the relationship between frequency, wavelength, and the chime length, which is our topic for today. Frequency and wavelength are inversely proportional to each other. So, the higher the frequency, the lower the wavelength, and vice versa. On the other hand, the length of the chime is connected to the wavelength. We use a square block that has the same length in proportion to the chime of a note to represent the wavelength of the note. And our magic formula here is that the area of the block, or the length of the block squared, is proportional to the wavelength of the note. Okay, now let's return to the yellow block that represents the chime of our lower C note, and the green block which represents the chime of our higher C note. Since the C notes are 1 octave apart, the frequency of the lower C times 2 equals the frequency of the higher C. And recall that the frequency and wavelength are inversely proportional, so the wavelength of the lower C divided by 2 equals the wavelength of the higher C note. And the last piece of the puzzle is that the wavelength of a note is the square of the chime length for that note. And if we rearrange the equation, observe that this essentially equates 2 volumes to each other. Substituting the known chime length of the lower C of 23, we can calculate the chime length of the higher C to be 16.26. So that is how we connect the lower C to the higher C. Now let's talk about the comparison of the longest chime with the second longest chime. Can you guess what note does the second longest chime produce? It is the note D, and we will use white blocks to represent the D note. So, Jack, how many stacks do we have there of the big yellow ones?
We've got 1, 2, 3, 4, 5, 6, 7, 8.
All right, and we got 1, 2, 3, 4, 5, 6, 7, 8, 9 of these. So we've got this ratio of 9 to 8, and again, same thing as we did before, we're just comparing volume, and now we've got 8 high instead of 1 high, but the volume of that stack equals the volume of this stack. And so if your goal is to figure out, well, how long do I make this chime? Well, you just have one equation and one unknown. Solve for D's chime length to be 21.68. Notice the ratio of 8 to 9 is actually a close approximation of 1 over 2 raised to 2/12. Remember how we deduced the relationship of lower C's chime length and higher C's chime length? We start from the relationship between the frequency of lower C and the frequency of higher C. Same concept applies here. We start from the relationship of the lower C and D. C and D are 2 notes apart. So that is why we multiply the frequency of C by 2 raised to the 2/12 to get the frequency of D. Inverse the relationship for the wavelength, and that's how we get the ratio of 8 over 9. Now, let's find the length of the third longest chime that produces the sound of note E. Notice C and E are 4 notes apart. So the frequency of C times 2 raised to the 4 over 12 equals the frequency of E. Inverse the relationship when we want to indicate the note in terms of wavelength. The length of chime squared is proportional to the wavelength of the note. And 1 divided by 2 raised to the 4 over 12 is approximately equal to 4/5. To compare the 2 notes in terms of volumes of blocks, now we are using 4 yellow blocks that represent note C and 5 orange blocks that represent E. And so this would be the length in centimeters of what the third longest chime is in inches. And now our ratio is 5 to 4. Yeah, so if we want to know, well, how long to make this chime, well, again, we use that same formula. We compare 5 to 4, and whatever length makes those volumes equal, well, that's how long you make that chime. Substituting the lower C's chime length of 23, we can calculate the E's chime length to be 20.57. Next, let's find the chime length of note G. How many pieces of block C and G should we use? Let's return to the musical scale. Note that G is further away from C and they are 7 notes apart. So multiply the frequency of C by 2 raised to the 7 over 12 to get the frequency of G. Follow through the same steps that we did before, and notice 1 divided by 2 raised to 7/12 is close to 2/3. Rearrange the equation to see that we got 2 pieces of yellow blocks that represent C and 3 pieces of light pink blocks that represent G. So we only have 3 of these, and we have 2 of these, and so we're at the ratio of 3 to 2, and if you know that ratio, it's 1.5. And again, we know what this volume is, and we can solve for this volume because we know we have a height of 3, and then this is how long we make that next chime, and that leaves us one more chime to look at. And here we've got 1, 2, 3, 4, 5, and we have 3. And so this would be the length of the smallest chime that's not a C, and so that would be an A. So this would be the length of the A chime in centimeters. And the ratio of 5 to 3 tells us how long that length should be because we need those 2 volumes to be the same.
Yeah.
So kind of cool, wouldn't you say?
Yeah.
Here is a table that summarizes the notes with their respective chime length. And notice that the ratios are not exactly equal to the exponential increase in the frequencies. And this is actually a much bigger issue for the music professionals than we may think. But this is a story for another day.